start streaming. Let's see if it works. Okay, sound test. Okay, sound test. Okay, it looks like we are good to go. Let me just pop this chat out. I forget how to pop it out.
Clean.
Pop out chat. How do I... Okay. Okay, so welcome Sebastien Avakian to the show. We haven't done one of these in a long while. So Sebastien is a second-year master's student in my old research group. So welcome. Thanks for coming on the show today.
Oh, excited to be here.
So I think a nice way to start off chats like this is to sort of talk about how you got into physics. Like, you know, what's your sort of earliest memory of being excited about physics?
Yeah, so I've always quite like when you start kind of going through high school or whatever, you always kind of start with you do science and you kind of cover different topics, and I always found that really interesting. And there was always a couple points of like, say, like really odd things like water boiling and like changing phase or whatever. And I always thought that was interesting. I was like, oh, that's cool. And I kind of took it as like a fact where you're like, you raise the temperature high enough, then you'll change phase. And at a certain point, we started getting to more and more complexity. Here in Quebec, it's like grade 9 and grade 10, where you stop doing science and then you do physics later on. And it was just really interesting to me that like I could not fathom that people came up with ways to explain why that would happen. I just thought it was a fact. And as we kind of got along and watching a lot of like Discovery Channel and like even as much as people like to bag on them, but like science communicators like Neil deGrasse Tyson or like Cosmos and Carl Sagan, all these people kind of just talking about it, and you're like, oh, that's interesting. And you kind of learn that what they're saying, like it sounds like facts in the sense that like you assume it to be true, but then as you kind of you see one little peek behind the curtain or one deep dive of like one equation, like I don't know, how do you infer that from this? And I just got interested. And then from high school then on, physics was interesting, but it was always quantum mechanics that was fun. That's like the easiest pull for everyone to get into. They're like quantum mechanics, spooky quantum mechanics, Einstein, all that stuff. And then in Quebec, you go to CEGEP. And in CEGEP, so I chose like the natural science path. You could do like the health science or like the physical sciences. Yeah. And I had a couple teachers in my education that really impacted me, that really like, I really admired the way that they thought and constructed and carried themselves. And either it was a dedication to rigor, like I had a mathematical physicist teach me linear algebra, and it was really interesting for that to be the case. And I was like, what is mathematical physics? And he kind of explained it for a bit and was like, you know, and the way that he would present things in his arguments and reasoning was something that I really wanted to learn. And it turns out that you can apply something like that to things like science. And that was really interesting to me. I had also my grade 10 math teacher was a physicist as well. And she showed some, like in class, he just pulled up one of his papers and was like, yeah, like I worked on this. Now I'm just a high school teacher, but like I used to work on stuff like this. And I was like, and the way that he would carry himself and talk about life was really interesting to me. And I wondered, how can you be in such a weird type of area of study and think about things in that way? And that was big for me. And then after CEGEP, I decided to do physics, and that was just, the rest is history in that sense. So it's people, I guess the answer would be people.
People, lots of interactions with people. That's really interesting that you say that your first, like the first memory that sort of comes to mind is when you're a kid and you're like, it's almost like many body physics was like written in your future.
Oh yeah, definitely.
With like boiling and phase transitions and things like that. That's really interesting. Like the people you meet along the way are always so important for your like love of like a topic. Like I had a math teacher that was also, well, it was actually a math tutor where like I really just didn't appreciate math, and then after getting help in a math class and being taught how to like understand mathematics and explore mathematics in a more like deep way. Like that was
Mm-hmm.
like that was it. That I was like, this is what I want to do.
Yeah. No, it was actually, in particular, the grade 10 math teacher that I had that was a physicist. It was one thing that really stuck with me. And whenever you're in education, you typically don't get the feeling, like especially in high school, that what you're learning is the final version of that thing. So like, for example, you'll learn part of some kind of history. So in Quebec history, like Canadian history,
right.
And you learn some kind of world history and medieval civilization, but you don't ever get the impression that like, this is how it always was. I have all the knowledge capable of something. And one time we were working on like on quadratics. And by the end of the quadratic bit, he was like, now you guys are all experts on quadratics. If anyone asks you any question about quadratics, like I've given you all the tools you need to reason to understand quadratics. You guys are experts on it. And I kind of stopped. I was like, no, he's wrong. And then the more you think about it, even as some, like when I tutor people or when I revisit these things, it's like, yeah, no, it doesn't get any deeper, at least at a level of like factoring quadratics or like whatever you want to do with it. But it kind of stuck with me. I was like, how can you have terminal knowledge about something in that sense? Like, that's so weird. And then it was kind of just like a matter of fact way of like, no, you know it now you can use it now, go and do things with it, you know? And that was really impactful for me as well. It's odd.
I guess I've never even that's never really occurred to me that you could sort of get to that point. But I guess for topics that you learn at least in high school, well, I don't know if I've learned anything since then that I would be confident enough since high school, like calculus. Could I really claim to be an expert on calculus?
Yeah,
I mean, I struggled a little bit in real analysis.
Oh, me too. Oh, it's so difficult.
Like,
so difficult.
Am I gonna like reason my way into? It's of course like a really interesting observation because you basically like, you know, eventually you're gonna reach some threshold for most topics, and like that threshold's gonna be much higher for what you do research in, of course, right? But I don't know. I don't know if I would ever feel confident enough to say that about something.
No, me neither. No. I wouldn't either. Especially at this point, like I think there's certain topics that you can teach in a very like self-contained way, and that's why they're taught at the high school level. Right. And quadratics happen to be one of them. Let's say, or you don't teach quadratics, but polynomials, right? Like even as you like, technically, it's also not true that like, you know, you're an expert in quadratics, but it was the sending the sense of like, you've learned something, now use it. And you know for a fact, like, or he can confirm the fact that now you've learned enough things to go on and move on with your life. True. You know, like that's such a weird distinction because like, I would never claim, especially because you're right with calculus, like I would never be like, yes, I can comfortably calculate any limit rigorously, you know, like I cannot, you know, or these weird things of justifying interchanging of limits or anything like that. I don't really want to claim that I have knowledge on. I will sit with my happy physicist intuition of everything is continuous and should behave nicely. So it should be so, you know?
Yeah, absolutely. I still feel, yeah. Things that I don't know about statistical mechanics or quantum many-body physics like occur to me daily, and I'm like acutely aware of lots of things that I do want to learn that I just don't. Yeah. I just don't know. Like we were talking the other day about these Lieb-Robinson bounds that give you like a finite group velocity for locally interacting systems, but like, and it's just so like everyone who does many-body physics should know about that. But I definitely don't know how to prove that. I definitely don't know how to prove it at all. Yeah.
There was a there's certain things that I think you should. It's hard to learn comfortably about these topics, like especially when depending on what philosophical take you want to use on like how you learn things or what we actually can know about these things. Like you can either appeal to some intuition you have or like or to some formal system or some formal type of theory that you can construct or whatever. But like I definitely agree with you. Like there's things like I remember we also talked about like the gapped ground states and the exponentially decaying correlations. And I was like, when I heard that, I was like, should I know that? Like, should that be intuitive to me? Like, yeah. I don't understand. And then I look up the paper from Hastings, and then it's like some like 20-page proof about it. And it's like, that's not going to give me any intuition about it. So like, you have to kind of sit there and make a story for yourself. And then I talked to my other friend about it, and he was like, yeah, you know, the gap like transitions to like 1 over the gap, and so the correlation length, and he had another story to go with it, but he was like, I'd never heard of that before either. So it's like a weird thing that you kind of go with. But once you've kind of made a story, at least if you take the position that like once you kind of have some intuition and you want to use that intuition functionally, you kind of have to assume you have to truncate at some point your questions about things, right? And you have to move on with them, or else you're never going to get anywhere, right? Which is the hard part that I had to learn about research too. It's tricky.
Yeah, absolutely. So a questioner says, could you speak about the topics you research? So we're definitely gonna get in there, and I hope as you see, like, lots of random research tidbits will come up in the conversation. But we'll definitely talk about what Sebastien does for research. So let's move on a little bit in sort of your journey to becoming a physicist and doing your graduate school. So as you're going through undergrad, like how do you settle on many body physics and condensed matter physics? Like I feel like, at least for me early on in my undergraduate school, like that type of physics wasn't even on my radar, despite it being the most common field in physics.
Yeah. It's kind of funny because I kind of did so. Okay, so initially, I did my undergrad in math and physics. So I had like, when you're very eager and you discover what physics is for the first time, and you're like, that's a thing, like people do that. And you start to learn more about it and get more rigorous with your studies, and you go through some formal kind of training. You tend to, at least in my opinion, a lot of my friends were very like purists in the sense of like, we only believe in mathematical beauty. We see, like these are such cool things. And you kind of take that like, not a youthful take, I guess. Not that I don't think that's true anymore, but it's less kind of prominent. And so I took a lot of like real analysis courses. Like I took up to analysis for like, you do functional analysis and all these things. And I was very, you develop a lot of mathematical competencies and you get quite competent, and you've structured math in your brain in a way that you can learn things for your own. And at first, like to me, that was fun. But the whole point of doing these things is to do research. And so the topics that I wanted to like pick up and I wanted to use all this cool stuff that I had learned.
Right.
And so the first thing that you think of is like, well, what's the most complex thing you can solve? I don't know why that came to me first, but for me, it felt like, what's the hardest thing you can use it for, right? And then you're like, oh, so I was because I'd watched like a lot of Cosmos and all these things. Everyone kind of loves astrophysics initially. I thought it was quite cool. And so in CJEP, I got the chance to do some research in astrophysics, and it was black holes. And I thought, general relativity is really cool. It's like people describe it as a fun theory, and there's some cool ideas in there. And at first, like I kind of did that, and I kind of saw the reality of like, it's maybe a little bit more coding than it is more formal theory. Right. And then I kind of shrank down a bit. And then during my undergrad, I got able to do some research in atmospheric physics. So I developed a model of like the atmosphere with some just simple math, kind of played around with some actually a fun use of the geometric sum. You can actually use it for like a really funny model of one layer atmosphere, and you can count, you can have basically kind of like a 2 probability sense of like, when light comes in from the sun, it could stay in the atmosphere. After it hits off the surface of the earth, it can stay in, or it can be reflected out. And there's a different probability for those 2 things. And basically, as you go along, you just imagine infinitely many scattering events, and then you get a geometric series essentially, because the probabilities are less than 1.
Okay.
So it's a really cool thing. And you can get some like really nice, really simple equations if your atmosphere is considered to be 1 layer, which it's not, but it's a good simplification to start with. And I was like, I didn't like the idea that when you throw numerics at something without having a reason to throw something at it. So a lot of the field was like they have these very fancy like radiative transfer models which solve like PDEs essentially, or partial differential equations. And that to me, I didn't feel like I could get any intuition out of it because I was solving it and then it would tell me what these predictions were. And I didn't like that. So I was like, sorry, go ahead.
So were they like big software packages that you weren't writing this stuff from scratch, right?
So I that's what the papers that I was reading and I got initially interested in, because I thought complex systems were cool, and like certain things about weather prediction. And I was like, I wonder how that kind of works with like physically. I wonder what determines that, because I think that's an age-old question of like, what's the weather going to be tomorrow? A natural question. And I was like, I wonder if there's some nice simplification you could do there to kind of really get to the heart of what determines these behaviors. And I didn't like when I dove into the literature, you can make some simple models, but they'd be like toy models that they'd use to explain some ideas, but they wouldn't put numbers to it. Mm-hmm. And so essentially I just Taylor expanded that set of equations, and it actually works quite well, believe it or not. To first order in like variations about some averages, you can actually quite well predict things like surface albedo and reflectivity and transitivity. And so all these things are really interesting and really fun, but I didn't feel like I was learning anything. Like I felt like I was mapping something mathematically to nature and then being like, here it works. And yes, there are some questions you can ask, and a natural question you can ask is kind of like, how does the reflectivity and the transmittivity affect each other? Are they correlated? Yeah. Because then that's a kind of question of like global warming, essentially, and radiative feedback in the Arctic, for example. It could predict that.
Yeah.
And so it could work, and if it was simple and it worked, that's quite interesting. And each term had different like intuition of like what things should be. But I found that was still too big, and I felt like I had no power kind of over it. Like I couldn't, if I came up with an idea, it wouldn't necessarily be me trying that idea. It would be me being like having to wrangle some data and then seeing if it panned out and have some assumptions. And I felt that like, and then eventually I got really, really small, and then I started working with condensed matter. And so I was interested in it initially because I stumbled upon like topological phases, and I was like, what does that even mean? Like, I just take an analysis, and like we talked about topological spaces and different topologies on sets, and I was like, what does that have anything to do? It turns out they're not really related, and directly at least. But it was these ideas of like invariance that really popped up. And I was in my last year of undergrad or before my penultimate year. And it was really interesting to me that you could talk about phases. I kind of returned back to that childhood, like temperature stuff, because you only really deal with temperature dependent effects later on. And when you do your undergrad, at least I found, like I only did stat mech later because I took a lot of math courses initially. And then I took solid state, and then I took quantum condensed matter. Those were all courses that like kind of slowly narrowed down. Like stat mech is really cool. And then I was like, oh, I wonder how you kind of escape that. Like they must have come up with like lattice models before then. And I was like, where does that come from? It comes from like solid state physics or condensed matter. And then what's the quantum version of that? Because we know that theory is better. And then went on to quantum condensed. And by the time I was doing quantum condensed matter, I was stumbling upon these phases. And then the Nobel Prize, one of the Nobel Prizes that happened was given to Haldane and the others. And I was like, what are these things? And they're like edge modes, gapless edge modes. I was like, that's what? What do you mean? How does that work? And since then I got hooked. And then I did some DFT stuff with topological states in a graphene-like substance called silicene. Mm-hmm. And to me, it's a very beautiful idea to quantify phases by just one index, or like 0 or 1, or like 0 pi or plus or minus 1. And things look the same, but realistically, there's like this long range hidden order that's there. It seemed like such a weird application of group theory and topology to something that has no right to be applied to. And that was really interesting. And I was like, that's so odd. I want to learn about it.
So do you want to give like an elevator pitch or sort of like a crash course? Like what are topological phases of matter? What are these phase transitions like? What's going on there?
Yeah. So phase transitions normally occur so what we're familiar with in our everyday life is kind of first order changes in, say, liquids. So for example, when you boil water, it's going to go from water to some gas. And usually what this happens by changing the temperature. And it turns out that you can also have similar kind of phase changes in quantum systems. So in systems in which you, instead of changing the temperature at really low temperature, so near zero, you can actually change a parameter, and your whole kind of system will change from being magnetic to non-magnetic.
And that parameter is like a parameter in the Hamiltonian in some sense, like some type of interaction that's happening between degrees of freedom, right?
Yeah, and so so functionally, that would be something that you would measure, like that would depend on the material. It would have a certain strength. So it depends on distances maybe of how things are arranged. And so in theory, what we do is we vary these parameters and take it for granted that we can do that. And we leave it to the experimentalists to find ways to actually do that. Right. But essentially, as these things are varied, we can actually have two different ground states or different lowest energy configuration system. And that's quite interesting because we didn't really change how the things were interacting. We were just saying how strong they're interacting with each other. Or in the case, maybe it's not entirely accurate, but anywho, it's because technically you can have negative and positive signs of, say, the Heisenberg interaction, and that could be ferromagnetic to ferromagnetic, which change the interaction. But for the sake of just exposition, it's essentially just telling you how strong something is. And to me, that was quite cool. And there's this way, the normal way the modern way that we understand it, and from the 1930s onwards, or 1940s, I believe, there was this man named Landau who came up with a way of classifying, how do we, what's like the deeper kind of view you can take of things changing phases. And it's about symmetry. And it's about how basically how something looks when you change it a little bit. And so it turns out that gases, for example, have a lot of symmetry in the sense that you can kind of move them however you want. It's still a gas. It's still rather interesting. And as you kind of cool, the symmetries get more and more, they get broken or they get lessened in a sense. So instead of having maybe the full crazy 3D symmetry, like you can spin it any which way, well, water kind of has to be like closer together, for example, so they can't be as far away, and it's still more or less free. When you go even colder and you go to say something like ice, it turns out that things are spaced at really very regular intervals. And that would be a way to distinguish between, say, water and ice, right? And so that's the symmetry breaking notion is how we kind of quantify phase transitions, roughly speaking.
Right. And
so what's cool is that in this quantum setting, you can also have phases that they actually go between. You can go from one phase to another by changing this parameter in the Hamiltonian, but they still have the same symmetries. And so the question is, like, how do you actually correspond? How do you actually understand that? How do you what's the difference between these two things? Because why would it have to change? Like the things look different, at least the wave function will look different. Right. And what determines, why do they still respect the same symmetries? Because classically our intuition should hold, right? Like the symmetry breaking idea is quite powerful. It gets you very, very far. It gets you extremely far. You can explain a lot of things with it. And symmetry is very important in quantum mechanics as well. So how do we go about qualifying these two phases? So there's a couple examples that are maybe kind of out of pocket, but the Kitaev chain basically is one example. Yep. There's the things I'm studying. So spin chains as well can have these symmetry protected topological phases. But really at the heart and the answer that kind of topological physics will give you is that actually it turns out that these phases, even though they have the same symmetry, it's possible they have a different topological invariant, which depends on some usually cool geometry that's really abstract. Like it could be the geometric aspect of, say, in 2D position space systems with momentum. It could be something like the Brillouin zone, or the possible momentum things can have in say a 2D solid. Turns out to be a torus, for example, in 2D. So actually the abstract space that the values that things can take because of the symmetry breaking is like a donut. Yeah. And that ends up being important, which I think is a really cool idea. And so it turns out that in these different phases, you actually have different topological invariants, and they're classified by the shapes, roughly speaking, by the shapes of these things. And it's not true for every phase, but there's some really classic nice ones where you can classify it that way. And that just really hooked me. That's really interesting. And so that's kind of like the hallmark. And this phenomena is usually associated. And the cool part about all of this is that whenever you change topological invariant, so if you go between these phases that look the same in terms of energy and have the same symmetries, but they're really in different phases or close in energy, let's say, and they have a different topological invariant, the only way for them to switch and to go between each other is for something like the gap of the spectrum to close, which tells you basically roughly how, okay, this is a little bit harder to say in an elevator pitch form, but the gap of a system is just the energy required to go from the lowest energy state to the next one. And it turns out that a lot of systems have some gap. So like metals, for example, don't have a gap or have a very, very small gap. Semiconductors have a medium gap and insulators have a very large gap. And why that matters is that when you give an energy to the system, then things will only happen if there's possible things to go into. And so depending on how large it is, you're going to affect what kind of dynamics you get or what kind of possible things you can get out of it. And so it turns out that the gap closing is very important. And so lost my train of thought on that one. But the edge modes. And so there's only ways for the gap to close. And when the gap closes, they become gapless. And so basically, whenever you switch between these two things, the gap closes and we get these gapless modes, which means they can be excited to arbitrarily high energies. And so you can have these things where like the inside of your, or like the bulk of your system, or like the center or inside of your material is one kind of behavior, and then just the perimeter is edgeless or gapless. So it's really weird to think about, because then that was like the Nobel Prize in 2018 was about topological insulators, which have like a core or like a bulk that's insulating, but the outside has these like propagating edge modes, which is just odd. Again, you think about it and you're like, that's just weird. And that was like, that's kind of like that hallmark stuff and those physics I just found so interesting. And it's just cool to me that you can have a relationship between these abstract geometric objects and very tangible properties that could host really cool physics. So the nice examples is that there's various things you can do with these systems, and you can create like a graphene, for example, a system of just carbon atoms in a honeycomb pattern. If you put two layers and you twist it, it becomes a superconductor called magic angle graphene.
Oh, interesting. I've never heard that.
Yeah. So it's like bilayer twisted graphene, and there's a specific angle. You make a moiré pattern, and it becomes superconducting. And there's gapless edge modes, and it's very, very cool. And those things, a superconductor is very interesting. But the big feature, the big feature of topological things is that these gapless edge modes are protected, meaning you can actually cut your sample and they would still happen because they're insensitive to these local changes. It's that the whole phase of the thing is in this state. So you can't just cut your system and then have it be destroyed. And that's a problem with quantum systems. They're very easily destroyed. Yeah. And so the more we kind of learn about these things, we can build things like quantum computers with something called non-abelian anions, which could potentially arise in some of the research that I look at as well. And so it's a really weird thing that could have a very fruitful application. And the second that we start getting on this quantum computing path and understanding decoherence and kind of working along and constructing quantum states in a robust way, then we're getting into some very novel, interesting things that we could do now, because now we can actually get our hands on these things even better than we can now.
Absolutely. So I got a question here. Could you explain what is boundary edge correspondence?
Yeah. So the boundary edge correspondence is the phenomena I said of the gap closing. So the best way to picture it is in a topological insulator, you have the bulk being an insulator. And so we'd call that topologically trivial, or say it would be it wouldn't be topologically trivial. It would be, say, topologically non-trivial. And this whole phase would happen. It would be along this insulator. And the gapless edge modes appear because when we go from our topological phase to a non-topological phase, we need our gap to close. And so when the gap closes, we have these modes or these states that exist only along the edges because the gap has to remain shut. And it turns out that both phases, basically, say on the inside of the insulator and on the outside, say that just the air or whatever, or just the outside of the sample, would have a different topological invariant, but they're both gap, let's say. So an insulator would have a gap, and a topologically trivial medium would also have a gap as well. And so because this invariant has to change, there's no way for it to change without the edges becoming gapless, because the gap has to close. So it's kind of like, if you can imagine, and here's the topological part too, at least in terms of the band structure or like how the energy looks across the sample, you'd actually have that the gap will kind of be like, make like two parabolas, I guess, like this. There we go. No, it's bad. Like this. No. Anyways, it's like imagine an upside down U and a normal U. And basically they would have to touch and then separate again. And when they touch, that thing is also localized in space. It's localized at the edge. And so we'd call that bulk boundary or edge boundary correspondence or bulk boundary correspondence, roughly speaking.
So this seems like a really hot topic right now. That's like a lot of people are talking about this in research. What would you say is the best place to start reading about something like this for a beginner? Let's say a fourth year student who has a decent background in quantum mechanics, stat mech.
Yeah. The best way would be to make sure that you understand solid state physics first. So it's really not that bad. It like a lot of the textbooks are quite terse, like the famous example is like Ashcroft and Merman. I think everyone in our group has Ashcroft and Merman. Once you get through, you don't have Ashcroft and Merman? Oh, slander. But essentially, you kind of just go through a beginning understanding of how lattice systems work. And what you want to get to is the point where you can understand that it's called, the famous theorem of its matter systems for real space things. What is it called? The translational, when you have translational and Bloch theorem. When you have translational invariance that's discrete, essentially, your wave function looks a certain kind of way. And it turns out that you get something like a phase factor, so just like a complex number, times something that's periodic in the unit cell. So in the pattern that gets repeated across your sample. And so if you can understand kind of how that phase actually determines the state of your ground state or the wave function of your system, a lot of the dynamics or how things evolve in your sample depend on something in the phase factor. It's called K, or the quasi-momentum, as we call it.
Yep.
And once you can understand the quasi-momentum properly, you can go on to understand the Brillouin zone, which is part of the reciprocal lattice, but roughly speaking, it tells you about what possible momentum you can have in your solid. And then you get into band structure calculations, and you learn what the band structure is. And it's basically the allowed energy states in a solid, and so, or something that has discrete translational invariance. And so, which means just it looks the same. You could just, everything looks the same, but only when you move by a certain fixed amount instead of an arbitrary amount that you move in.
Right.
Like say free space, or like just nothing. And so you start by first kind of understanding just band structure, and that is very classical. So it's quantum mechanical, but it's semi-classical in how it's kind of approached in most textbooks. Like they'll do something where they won't actually solve the Schrodinger equation in K-space. That's something you kind of do later on. What they'll do instead is they'll do like semi-classical things. Like they'll say, okay, so why don't I treat this quasi-momentum as the momentum of like the electron? And it's not exactly true. It's not precisely true. It's true modulo some reciprocal lattice vector, or some jump that you can do in the reciprocal lattice space. And so once you understand that, then you move on to the band structure. And then you go on to understanding what's topological band theory, or what do we understand? And so then the next ingredient that you might have actually encountered is then the adiabatic theorem in quantum mechanics, which means that if you slowly push your system with a parameter, so remember we talked about varying parameters for a phase transition, turns out that there's some systems that you can vary the parameter very slowly. And it turns out that solving this isn't actually that hard, whereas to any physicist, you think of varying anything and you have to think about like, okay, is this easy to do or is this hard to do?
Yes.
And adiabatic theorem is it's easy to do if you go low enough, if you do it adiabatically. So you just push your system very slowly, you change the interaction very slowly. Or in thermodynamics, it would also be just kind of adjusting the pressure and temperature very, very gradually, making sure you stay in equilibrium. It's the same idea. And after you understand that, then we get into something called the Berry phase. And then from the Berry phase, you start understanding things like, now, what if you do this adiabatic push, but in a cycle? And it turns out that when you undergo a cyclical change in the parameter, you can actually move your Hamiltonian in the space of parameters. And you start understanding the shapes and the possible geometric arrangements you can have in that space. And it turns out you can actually measure this with something called the Berry phase. And it's something basically as your wave function gets moved along in this parameter space, it picks up a number. And this number depends on not the choice of path that you do. So it doesn't depend if it's a wiggly path, as long as it's open or closed, for example, whether you kind of stop or you return to the same point, that'll actually matter. And so it's a really nice thing to go from there. And then from there, you can start to understand topological insulators very briefly. And that's your best introduction to it. The thing that I study now is more with spin chains, and you kind of get to more varying levels of complexity. And then the same phenomena pops up. Then you get bulk boundary correspondence and all these things that kind of naturally appear. But that's like the best way, probably topological insulators, because it's the most familiar to you. It's the most natural thing you can go on to look about next without having to break the bank. You can even solve some of these things by hand. It's quite nice. So
when I first met you, when you were coming into your master's, it seemed like you already had quite a good idea of like some of these topics. So you had formal courses in a lot like that exposed you to a lot of these ideas, right?
So the only topological stuff I was exposed to was during the research that I did. So during my undergrad, I did a lot of research. And so when I did the silicene stuff, looking at edge states in there, I kind of spent a lot of time just reading papers, and that's the hardest part. You just kind of got to get your foot in the door. And so you just really got to spend a lot of time reading, and that's tricky. And you have to palette it. And what really helps by doing that is getting the most out of your coursework. So I was very fortunate that I told you the sequence of like stat mech followed by solid state physics followed by quantum condensed matter.
Yes.
So that progression is a very natural one to undergo. The quantum condensed matter course was a grad course. I took it a little bit early, but the teacher who taught that also taught quantum mechanics the year prior. And so I was more or less kind of familiar with the style.
Yeah.
So I was able to kind of go along with it. And so it was very natural. It was kind of, you also learn a lot of quantum mechanics at the same time. So it's many body theory. It would be, I guess it wasn't a formal many body course. It was kind of just seeing like a many body magnetism, many body like Hubbard model stuff, and then Fermi liquid theory. And we kind of just went through that. And
that's
from there, I kind of used that coursework as a strong, they're good.
I was gonna say like that's very sort of like fortunate. I guess like when you have people ask you like where should I go do my undergrad, one of the unfortunate parts of that is that when you're starting out in first year, you have no idea what you want to do, what you're gonna want to do in 4 years, right? But then the only time it really, in my opinion, the where you go for your undergrad matters the most in fourth year, because that's where you have specialized courses.
Yes. Yeah, and in my university department didn't have a large many body group. It's like at McGill they had a really like big astrophysics group, but the people that were there in many body physics were very, very good. And so they ended up teaching, say, quantum mechanics courses. So when they would teach, so I learned from them, and when they would teach things, they'd be like, "This is useful in what I do." I'm like, "Oh, what do you do?" And they're like, "Oh, I do many body theory," and like they kind of give you little tidbits, and you're like, "Oh, that's what it's used for." Because it's not that it's rare, but you don't see people just use bare quantum mechanics on things. Now it's quantum field theory, or you use some like weird stuff for stuff that I don't know about for physics. And it's possible that you can do maybe some cosmology with it as well. I have no idea. Like maybe for neutron star calculations, even then. But it's a really, I kind of knew I wanted to do by that point, like at the beginning of my last year, I knew I kind of wanted to do many body stuff. I just needed kind of an example. Like I spent the time reading about topological insulators and stuff like that. And I kind of chose my coursework to suit that. Like I knew that I was good and liked quantum mechanics, and I wasn't that into QFT. And the people that I talked to that taught me about quantum mechanics were people who were also many body theorists. And it was very fun because of it. And so, yeah, it was fortunate in a sense, and I got quite lucky with that, like that break in courses. But at the same time, I would say a lot of the math courses, like real analysis, was a big game changer for me. Like you really, it was the first course I really struggled with, and I was always like I was good at physics, but like math wasn't necessarily my strongest suit. Like I don't think I'm a very good, I wouldn't make a good mathematician. I wouldn't. But I've learned the language of real analysis, and like I understand how to, like I know how you would structure your argument. You know what I mean? And the creativity or natural tendency for abstraction doesn't come that naturally. But I can speak that language. I can work with it, and I can understand it, and I can digest things from it. And that to me really helped, because then when you, in your last year, you need to kind of, it provides you a tool to start deciphering things for yourself. And then you're like, okay, what is this thing? What do they do? How does it work? And like, do I want to do this? Maybe not. What do they do? You know, and you just have to structure things that way, which is quite tricky.
So okay, that's interesting. So your day to day, so you do a lot of numerical work. Can you sort of talk to me about like what's a day to day research like for someone doing your topic?
Yeah. So day to day, it goes between, so research wise goes from like 2 to 3 things. It either goes by usually starts with reading some kind of paper, or not necessarily a new paper, but it's one that I've been thinking about. So I kind of take a while with at least interesting papers that are relevant to my research. I spend a lot of time just trying to make sure that I understand context in which I'm operating in, and the language that we speak, and language in air quotes as in what are some assumptions that we make when we work in what we do. So, for example, we work with ground state physics. We talk about, like the other day where we talked about the exponentially decaying correlations. That was something that I've been thinking about for a while, and making sure that my context and setting for the research is correct. And usually I find it best to kind of start the day like that. And I also like to learn new things, like formal stuff. And so you have to learn also, I'm trying to get better at the framework of what we're using. So now, while I talked about topological insulators, I work with like spin chains and I do numerics, like you said. Yeah. And so a lot of that has to do with, it's still theory. As much like numerics doesn't mean that you just plug things in. It means that like you do very specific things that you plug in. And so I need to know all the manipulations that I would do on paper. I just, instead of writing down the calculation, I need a computer to do it for me. But otherwise, the steps that I'm doing are what you would naturally do in any problem. Like for a wave function, you'd try to find the expectation value of some observables. You'd play around with it. You'd ask yourself questions. And then there's like the science element on top of it of like, what questions are you asking for your research? And that I find is best suited when you do like a mise en place or like a context to your research. So I start with that. And then I move on to whatever goals I have for the week. So every week after I meet with my supervisor or my supervisor and your former supervisor, with Eric, I come up with some goals that I want to reach for next week. So when you start the project, you just have to learn things, start asking questions. And then once you've asked a couple of questions, you start working and you work with your playground that you have. And you usually have to write your code and get everything set up. And once you have something working, you can just ask questions and go. To do that, once you've asked your questions, then I have some goals that I kind of set. So right now we're trying to finish up the current project that I'm working on. And I try to I order every week I have an ordered list of how I am going to attack these problems and or these goals that I want to achieve.
Like you write down goals at the
yeah.
beginning? Oh, that's interesting. I definitely don't.
Yeah,
that's one way.
I do at the end of the week. So but it's from the previous week. So like on Fridays, I'll end up writing all the goals for next week. So when I come on Monday, I'm like, perfect, this is what I'm doing, and I start on Monday. And so I'll read a bit and I'll look at my list, but I'll order it as like on Monday, I'll do things that are like really easy. So like I'll do like, for example, I'll get all the easy calculations out. Then I give myself the most amount of time to work on things that I know I'm going to have a harder time with because I know myself. So I'm like, I know this is going to be trickier.
Yeah. I've never thought to like talk to people about how they structure their research week, because I just I do what I'm interested in at the moment. I'm very I'm not structured at all.
Yeah, but the problem is that if I do that, I get nowhere because I'm too curious. Like I'll be like, oh, I'll learn about QFT this week. You know what I mean? Like I'll sit down, open a textbook, like, oh, this is cool. And that's why I also do the reading. Like reading the paper that I might read before I start doing my work in that day might not be related to doing. Like I like to have the paper out, and just before I start my work, I'll just read it really quickly and go like, oh yeah, this is what I was working on. But otherwise, it could be some weird like, I don't know, it could even be not physics related. Like I'll just learn stuff. And when I take breaks in between of doing my research, I'll look at that and kind of look at like fun things. Like I look at your papers too, because they're really fun. You're just like, what are you talking about? You know, like this is so interesting. And then you just learn about new things that way, and you ask questions, and then you let your brain guide you. And I find that it's in the times where I'm not working that I'm really creative. So then when I'm like breaking out lunch or after, or like at night, I'll be like, oh, try on this tomorrow. Or if I'm playing a game, I'll be like, oh, what about this? And then I'll explore that and kind of go down that rabbit hole. But very naturally, I try to stay contained or else I get too lost.
So Beck says, you don't work on weekends and Friday and end Friday and start Monday, ? Interesting.
I try to. I really try to. It's usually
really
on Friday evening, sometimes start to finish off. Yeah, it's
really
tricky. It's tricky because, and especially the last couple of weeks, I've got a lot of progress out. And so when it comes to being like, I'm going to stop working, that's really difficult because you're like, no, I'm on a roll. Like I'm flowing, like things are good. And so to address like the last bit, and then I kind of, after I'm done reading the papers, I set my goals, then going between writing down diagrams and just doing like little calculations on paper, and then basically coding and checking out output from my calculations and just kind of thinking about what the output's supposed to be. and stuff like that.
I don't know. That's really interesting. Like I do think about my workflow. I do think like, you know, like these are my priorities.
Yeah.
But I that's as far as it goes. I think about what my priorities are, and then I prioritize based off of that. Like if I'm gonna set aside time, it's gonna be something I set aside time for things I don't want to do, like writing it. Like the worst part of research by far is writing papers and making plots. That is literally the worst part about research. And like on Monday I know I am responding to a referee, and on Tuesday I know I'm writing a document to send to like a potential collaborator. And that is like the extent of my planning. And then Wednesday through Friday, I hope I can just do whatever I feel like that day.
Yeah. Well, I guess like I get that, because there's some like it's more or less a guide. Like I have goals for the week, but it doesn't necessarily mean that I'm gonna hit all those goals, right? Yeah. There's this one thing about like wanting to do it and then like actual execution. And for my like what normally happens is that I don't set like a very direct list of things. Like for example, I'll be like, I want to finish this. I want to learn about this, and then I want to. So like an example could be, I want to. So it could be some really boring things like restructuring my code. Like I want to just reform. I've done that maybe once or twice, but like it's been on my goal list for a while. And I'm like, oh, I don't feel like doing it, so I don't do it. But like I give myself some goals to work with, because or else if if my end goal isn't very precise, at least for when it's not the problem solving phase, but just like the workhorse phase, which I don't know. I define there's like times where you need to trudge through it, and the times where you need to be creative. The creative parts are really fun, but there's also parts you need to trudge through, especially when you're doing numerics. I find like you just need to get some of the stuff through.
I love the restructuring your code thing, because for me, I have quite literally never done that because because basically my guiding philosophy is that as soon as it works, like I might do a Passover to make it more efficient, but like ease of use, it's like legacy code just works. And then if there's other code that I could improve upon, I improve upon it in the next project. But like, so there's like quality of life things that I've implemented for projects that I'm starting now. But then like there's old projects that are like super inefficient about the way like I set up the problem, and I still go back.
Yeah.
I still go back and use the extremely like inefficient and like silly way to do it. Like every time you change a parameter, you have to like recompile the project. I still do that for some projects, and then I go to the new ones that have like fancy, you know, you get to like input it in a much more efficient way. I don't know.
Yeah, no, like I have that too. Like, don't get me wrong, and it's I've only done it once or twice for whenever there's a bug. It's like but like what I mean is like I haven't touched my actual. So like I do IDMRG, and like I haven't touched my my core MPO and everything. Like I haven't touched any of it. The only thing I kind of change is like the second half of the code. Like for example, I take the same like the legacy code like you're saying, and then I'll save it under a different name and then just add something new to it. So like, for example, I have one for correlators. I have one for correlation lengths. I have some for like finite DMRG calculations for other things. And I just kind of change it as need, or like a vector and scalar chiralities. Like I just kind of keep the top half and then just cut the bottom and then do something new. So I know that part's efficient but I've worked on it enough. So like, I know that it's good. But the problem is that like, at least for my calculations could be quite long. So if it's not done efficiently, it's quite painful. The only thing that's not efficient is the eigencode, like my exact angulation code. That is what it is.
What's wrong with your exact diagonal? Is it just because it's a naive? It's like a
it's just slow. It's just slow. Yeah.
Yeah.
It's like n equals 12 and n equals 14 max sites. So like it's not.
Yeah.
Like I wouldn't feel comfortable being like, yeah, let me crank it to 18 and like I know it's pushing it, but it'll be fine. Like no, it's not going to be fine.
That'll max out your computer for sure. N is equal to 18. What is 2 to the power of 18?
Something large.
Something 2.
I know 2 to the 14 could be 16,000 by 16,000. So it could be something ridiculous.
Yeah. So 32 gigabytes I've found. Like if you wanna diagonalize a matrix and then do things with it, 32 gigabytes gives you um 26,000 by 26,000, and like that's the limit.
Oof.
Yeah.
Yeah, and it doesn't help that a lot of my systems have some periodicity. So I technically wouldn't recover some periodic or near thermodynamic limit things unless I really cranked it up to more. And like the only sites, like the only sizes I have available to me are like 4, 8, and 12. 4 and 8 are done in a couple seconds, and then 12 is done in like maybe 3 minutes or 2.
Someone is writing inappropriate things in the chat. I don't know how they got here. I don't know how to ban people. Okay. Okay, hopefully. It's only for 300 seconds, though. Okay. Well, okay. So, maybe okay. So while I'm trying to like permanently ban this person, can you briefly explain what I think DMRG and IDMRG are like really cool algorithms? Could you break down what DMRG is and then how IDMRG is different?
Yeah. So DMRG is the density matrix renormalization group. So this came out. So this is based on the idea of someone called Steve Wilson. Steve White.
Yeah.
There's a lot. There's Wilson RG and then there's White's RG. So White came out with a paper in '92 of an idea of basically being like, if we want to get access to solve these hard problems, like say the Hubbard model and problems that don't have an exact analytical answer, what we can do is we can just like grab, say, a 4-site chain and then keep basically opening the cell and then putting 2 sites in and then solving the problem again and kind of expanding a chain like that, say, of a couple of sites. And now the problem is that this will like exponentially grow. So the issue is that so as we were talking about earlier, like this 2 to the n business is quite a problem, and with spins at 2 degrees of freedom. So the local dimension is 2. And as you just get n of them, you get 2 to the n states, and 2 to the n blows up really fast. So the sizes of the matrices that you're using get quite large. And there's a lot of memory, and then it becomes intractable at that point. And so one of the ideas for DMRG is that why don't we, instead of like kind of allowing this exponential growth to occur, why don't we be very clever and use something called the density matrix? And so what you do is every time that you solve this problem of adding in 2 sites, you have a block and then the environment, and you solve how the block impacts the main block interacts with the environment left block and the right block. So it comes a couple problem, and these things can get quite large. And every time this would kind of just grow exponentially, but you can keep the size of the states finite by truncating the density matrix essentially. So what you do is you can write your state on the system as a Schmidt state, which basically cuts your system in half.
Sure.
So it's basically you come up with an orthonormal basis of the left and right sides of your system, roughly speaking. And you can then diagonalize this thing, the density matrix, after you formed it, and you'll have like basically some eigenvalues that occur. And what you do is you only keep the relevant ones that matter. And there's also the added like caveat that when you actually diagonalize the density matrix or the reduced density matrix, whichever one you're using, it's related to something called the singular value decomposition, or the SVD, which is numerically very efficient. And so this happens for a particular case. A ground state can actually be truncated, and so you can keep the size of your system finite at every step instead of having this exponential stuff. And this is reasonable, not just because you can't just truncate anything because you feel like it, but it's actually because there's a cutoff. You can actually control the accuracy, so you can actually push and vary this size of the states kept, so you can keep the accuracy kind of your overall system. Now, this is done in the finite limit, and now as time has evolved, we've kind of come up with a really structured way of doing it. So functionally speaking, that's like the intuition of like physically of doubling the sites and then truncating the states, and keeping only the relevant ones that have the most weight, basically probability weight into them. And this is very naturally related to things like entanglement entropy because of that, because we have the density matrix and we have the Schmidt decomposition. We naturally can get von Neumann entropy out of that with the eigenvalues. So it's like a really convenient thing, and quantum information also plays into that a bit. And now how the algorithm has evolved is now we see this intuition as a specific guess of the wave function. So now we say that the wave function is made of something called a matrix product state, at least in one dimension. In higher dimensions, say 2 or 3 dimensions, you can have a tensor network instead. And tensor networks are like generalizations of matrix product states. They have a different architecture, we call them. And what effectively it means, though, is you put a matrix on each site. And depending on the specific sizes, you can impose on these things. You can get quite large and you can be quite accurate. And DMRG essentially just changes these matrices as you go along. It sweeps across your chain, goes to the left and to the right, and it optimizes them so that it minimizes the error, essentially, in your Hamiltonian. And so that's the finite DMRG. But the IDMRG still uses as a matrix product state as its ground state, or its guess, its variational ansatz. But now it's closer to this idea of like doubling the system. So in the first case, like I said, yes, you keep doubling the system and you truncate it. That's the general philosophy of DMRG. That's the renormalization group of the density matrix part, the DMRG. But in the IDMRG limit, it's slightly different. So here what you do instead is you want to get the infinite limit. So now we can't have infinitely many matrices. That would be intractable. So you want to get something that's translationally invariant. So what you do is you start off with like, say, 4 sites, and you keep doubling it. And you keep doubling and doing this thing again. So we actually whereas in the first case, we just kind of apply the Hamiltonian to our system, and we do some complicated optimization, and we can get these matrices, and it just kind of spits it out. It could be 60 sites, 80 sites, whatever. In IDMRG, we'll have, say, a unit cell of maybe 1 or 2 sites. It could be 6, it could be 12, however large you want to make it. And it effectively will keep introducing this unit cell and doubling and doubling and doubling, keep truncating. But what it does is that at each step, instead of being like, I'm just going to make the matrices better, what it does is that it introduces at the next step a guess of what the wave function should look like. So it's saying, well, if it's supposed to be infinite it's supposed to look infinite in the large n limit, and we're supposed to get some translational invariance, then why don't we give it a guess kind of to help the matrices along every time, instead of optimizing it just purely by optimization. And you get into this state that is translationally invariant in some unit cell. And so it effectively lets you know about properties of your wave function in like an actual sample, not just in like an arbitrarily small one with periodic boundary conditions. It really emulates kind of long range interactions that could possibly occur within your cell in an efficient way. And so, yeah, that would be the best way I'd put it, roughly speaking. And they have the same philosophy. Finite DMRG is used quite often when you add periodic boundary conditions, meaning that you relate one of the end sites to the other end, kind of wrap it around on itself, which kind of mimics a really long system that's just the same thing. But it's not quite the same. It's not quite the same. And this infinite limit really does kind of, it acts as if it really is a repeated version of itself, and it doesn't wrap around on itself eventually. And as you grow longer and longer, you have no more edge effects, basically, or of weird kind of behaviors at the ends of things, because it's effectively edgeless in that sense.
Right. And so what was the model again that you said you were applying these algorithms to?
Yeah, so I work, so it's the Heisenberg gamma ladder. So it's basically, you kind of make a ladder of sites, and I work with 2 interactions that are important with spin systems, which are the Heisenberg interaction, which if you roughly think of each electron as being like a magnet with like a finger with the direction where it points in, with a negative positive pole, it just basically says whether this is favorable or this arrangement is favorable, and it kind of dictates if they want to align or anti-align. And then I have something called the gamma interaction, which is hard to motivate physically, but it's so in a full fancy speak, it would be a full-on symmetric off-diagonal exchange of spin components, which means it'll couple, say, the x and y components of the spins. And it does so in an anisotropic way. So depending on which bond you're on, you get different versions of the interaction. So there's like a pattern that repeats in the unit cell, but it's kind of hard to motivate physically. It happens because of in certain materials across these planes that form in the material, like in alpha ruthenium trichloride, you can get these really weird spin orbit couplings, and effectively the interaction boils down to this gamma interaction. Yeah, it's very weird, and it's one of those things where it was kind of worked on by the Kitaev honeycomb model. It's like really inspired by that, in that basically it's like an icing interaction, but depending on the direction, it couples differently.
Yep.
And so it's anisotropic, and it's in that similar class of interactions, except that instead of being, say, coupling the both x components in one direction and the y in the other direction and the z components in the other direction, it's just like xy plus yz, and then zx plus zy in another direction. It's very weird. So it's hard to motivate physically, but it's a relevant interaction that has been shown at low temperatures in experiments to be important. And so we don't really understand what it does. So like the Kitaev example, like in the Kitaev honeycomb model, Kitaev just kind of stared at it and just solved it. And he was like, yeah, this makes sense. I thought everyone knew how to do this. And you can show there's some really cool stuff there. And we haven't really found an experimental version of that yet. And so my research is kind of interested in understanding what is this low temperature ordering, and does it actually is involved in these topological phases of these spin systems.
So it's characterizing the models to try and then try to map that to potential like actual physical systems.
Mm-hmm. Right. Yeah, and there's just that at low temperatures have been shown to have these interactions, and it's another case of can these be engineered physically? That's another question. But realistically, it's just kind of exploring, well, what if you have these two interactions together? What happens? Because it's like you always get like the Heisenberg Kitaev ladder, the gamma Kitaev ladder, and they always kind of use the exactly solvable point of the Kitaev model as a starting point, and then they kind of vary the parameters again, and then they see what happens. But they do Kitaev, gamma, and Heisenberg in a magnetic field, but they don't really do Heisenberg and gamma together because they're just assumed not to be special. But the gamma one is quite weird, to be honest. It's a very weird phase. Because that gamma ladder is odd. In
sort of quantum dynamics or non-equilibrium physics of like many bodies, integrability is like a huge thing. Like it changes the physics like very fundamentally. Is that something that is integrability a big issue? Like is it interesting to say? Would it be something you could say where like it's more interesting if something is non-integrable in quantum phase transitions? Like in this field?
I don't know. I honestly don't know. Because like in this case here, it could or could not be. I think that's kind of the question, really. It's like it's great and all to numerically work on this, but will it be fruitful? Is another question entirely. There's so in some sense, I guess at least functionally how I'm approaching this is that I'm curious to see if there is something to be said about that here. So does it actually matter? Like, do we need to have analytical results? Should we stay within that realm, or can we kind of leave those bounds and see what lies beyond there? If there is, like, I don't think I have any expectations for the moment, but it could or could not be fruitful in that sense. And I don't think I would have an intuition for that, other than in this case, this is really escaping the integrable limit. So I would imagine that I think at the end of this project, I could probably answer you.
Okay.
But for the moment, I'm unsure, because I don't know how. So in my personally, when something seems too good to be true in theory, I just tend to avoid it. So like, for example, a toy model is like nice. It's great to play with, and it can give you a lot of insight. It can tell you, like, for example, I know for a fact in a toy model, this mechanism is responsible for pairing. Let's say for Cooper pairs, for example, for BCS theory. You're like, yeah, if I have a slightly attractive interaction between electrons, I can have Cooper pairs that form. Right. And it's a toy model. It's not like this was done like it ends up working out for a nice class of materials, but like it's not necessarily in the functional limit. Like you can't just naturally just get a superconductor, and you can't just induce BCS pairing like super easily, like in your everyday objects or even in a lab. So in this case, we're wondering the question of, well, there's a toy model that's interesting, and it's the Kitaev honeycomb model. That's the one that can possibly host non-abelian anions or things that you can use to make quantum computers. And that's the thing that people are excited about. Now, it turns out that it's kind of hard to just get a Kitaev honeycomb model, or to form a Kitaev spin liquid is the other one, the other name for it. And so, we'd ask ourselves, okay, so if I can write something on paper, can I then go find it in nature?
Right.
And so far, they haven't found one. So they're like, oh, well, maybe it's not just the Kitaev interaction. Maybe it's this plus something else, right? And so they're like, okay, so for example, I told you about alpha ruthenium trichloride. That one is exciting because it would just be Kitaev and then maybe the gamma interaction and maybe some Heisenberg stuff with it too.
Oh,
so it's like which
candidate? There is a good candidate.
There are some candidates. There's a paper on it that says that they found a non-zero thermal Hall coefficient in their sample, which is the it's the topological effect of Majorana fermions, which would occur in the Kitaev honeycomb model. Okay. So it would be some signatures. But funnily enough, in 2019 or 2020, there was a massive drama in the field of Majorana fermions where some people were either fudging their numbers. So one group was fudging their numbers, and the other group was they misattributed the results to Majorana fermions. Because if you find these things, you're like, that's crazy. If you can if you can experimentally verify Majorana fermions, that's like, you've done something big here. This is a big deal.
Yep.
And so one expert who's been kind of like really focused on Majorana fermions kind of wrote a paper kind of like slandering them, not like out and out slandering them, but he kind of explained to them why they were wrong or why their data was impossible in those papers. And he then wrote an open letter to Nature being like, I think it's really sad that the people in this field are doing this and everything. And so it's quite hilarious. And there's a whole beef about it. And it's a really interesting thing that people are kind of doing that. I mean, it probably is a money pit. It's probably something that could attract a lot of interest because it's that kind of the technological advance you could get out of that is quite significant, I believe.
Yeah, of course.
So I can imagine why they would want to fudge the numbers, but you're going to get caught at a certain point. But I
can see why it's tempting, but I don't know why. With how rigorous science is, at least in physics, you must know that you're going to get caught.
Yeah, for sure. I don't know why they thought I could get away with it, but it did. It happened. It's quite funny. Yeah, so for example, we don't know if those, say, the Heisenberg gamma interaction is responsible for X, Y, Z. They're so complicated, and the phase diagrams are so intricate and not they're not nonsensical, but they're not intuitive necessarily. You look at them, I think Eric has one of those papers where he did a full Kitaev gamma, Kitaev gamma, maybe even a Heisenberg interaction, or just Kitaev and gamma, and he added a magnetic field, and you look at the phase diagram, and it looks like an explosion. Actually, it's crazy. And you don't look at that and you're like, yes, I understand which interaction is responsible for what. It's very messy. And, I think the next guess you'd say, well, if I can't find my toy model, can I perturb it, right? Natural question. Can I do perturbation theory on it? Can I then, maybe I could do numerics to kind of push past the exactly solvable point. Maybe there's a reason why I can do that. And numerics usually work quite well even for toy models. It's quite extremely accurate. So why not? And then you can ask yourself, okay, well, is it possible to have two other interactions that could even do that? And why don't we just take the other two interactions that weren't responsible, that we don't think are primarily responsible for the pairing, right? And those two interactions have been shown to be interesting experimentally. So I guess that is the question in some sense, right? Will it end up being fruitful? Who knows? Is there something to be said about it? Possibly. I don't know enough theory about integrable systems to know kind of back of the hand theorems that I could tell you that would justify that. But my intuition is kind of I don't know. I really have no intuition for these things. Yeah.
That's definitely fair. So I think when I invited you on, I said an hour. I think it's been like an hour and 10 minutes. If you still have time,
Yeah.
we can switch over to the physicist versus physicist segment. If not, we can wrap it up.
Super down.
Super down. Okay.
Let's do it.
Let's do
Yeah.
it. So I will invite you to the first game. It's gonna be a game of rock, paper, scissors. Where's chat here? Chat. Very high skill game. I wonder how many rounds this goes. Don't look at my screen.
I'm not. I'm not.
Oh, it's out of 3. It's out of 3. Okay.
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 Are you ready?
I made a pick. No. No. You read me like a book, dude. No. Okay. We gotta do this. Best 2 out of 3. Best 2 out of 3.
Okay.
Okay.
Yeah.
Okay. I don't like this strategy, Seb. This is kind of toxic. Yes.
No. Yeah.
I'm on the board.
That...
I'm on the board. Yes.
Mm.
I'm in your head. No, you're
No,
in
you're
my
not.
head. You're in my head. Okay. Yes. Okay. Okay.
All right. Last one.
Last one. You're a little toxic, to be honest.
You have to be.
You have to be. You do have to be toxic at a game.
You have to be. You have to be. Oh, I don't know.
Yes.
No.
No. Okay. No. This is it. This is for all the marbles right here. I knew you'd do it. I knew you'd do it. No.
I debated you.
Yeah.
All
Nice. Okay, so let's
That's
switch over to game number 2, Battleship. So Seb's up 1-0 on me. Did that work? Are you in here?
Yeah, I got it. Yeah.
Okay, so we gotta set up our.
Oh, the grid. Okay. Oh, interesting. I haven't played Battleship in a while. I haven't played Battleship in a very long time.
What is the most?
Is there an optimal setup? I guess it depends how you guess, right?
I feel like a Monte Carlo would be the best way
Yeah.
to guess. Like having no bias in the way you guess would probably.
Work out the best initially, and then you can pinpoint it.
Yeah. Okay. I am set. I'm set.
Okay, do I just press play?
I'm gonna press play. Let's see what happens. Opponent. Okay. Do I go first? Okay. Randomly selecting. Boom. I don't know what that means. Did I hit something?
No.
Oh, you got
Oh,
me.
it says X though.
Oh, you got me right off the bat.
Oh, I get to go again?
I think you get to go until you miss. I think if I play this game again with another physicist, I will create like a Monte Carlo. What is it, like 10 by what's A through J, whatever that is. I will create a Monte Carlo simulator. Okay, I'm getting wrecked. Oh. So did you get 2 shots in a row there? Or like, what happened?
Yeah. So every time if you hit something, you can keep going. Yeah. Oh, nice.
Are you
No,
cheating,
okay.
dude? You're cheating. Like, you're actually cheating.
No, I promise.
I never thought I'd get stream sniped on a...
I never miss.
No shot, dude.
Oh, no, I missed.
Oh my god, I'm getting wrecked.
Your random sampling needs some fixing.
Dude, where did you
You missed again?
Where did you put these things?
I'll show you my screen later. I'll show you the screen later.
Is it my turn? Oh.
Yeah.
I get the pleasure of missing again. Jeez.
Yeah.
Okay, you keep missing too.
For now.
Oh my god.
No. Wait, what does it say? What are those dots?
Those dots mean it's not there.
Oh.
Oh, I hit something. Okay. Do I get to go again?
I think so.
Oh, okay.
Yeah. Okay, wait. So when you hit and you get those dots, which means that it can't be there?
Yeah, I think so.
Okay.
We should develop a quantum
Interesting.
battleship game. I wonder what that would be. I guess you would be like you could have like a cat state, and it would be like your boats are in superposition or something like that, right? I guess that's what it would be, right?
I guess so. That's funny.
Are you just
really funny.
always in the corner? Is this what this is? Okay. I think we're tied now, right?
Yeah, we're tied. I've been missing consistently.
Oh no.
Yes.
Oh no.
Yes. Yes. Oh.
Okay. So I got that one. It'd probably be easy to like actually make a quantum mechanics battleship game.
Yeah. And like what's the like what is quantum about it? You mean the position of the superposition? Yeah.
Yeah, superposition. So once you measure a battleship, it would change the state of your board.
Ooh.
Oh no.
Interesting. Yeah, that'd be funny. That'd be really funny. And it's like an evolving thing.
Yeah, I wonder how deep you could I wonder how complex humans could like make states for the battleships. That's actually an interesting thing to think about. Like, what's the most complex way you could allow human beings to like set up a battleship game?
Yeah. Oh, there's ones, eh? Yeah, I guess so. You could also what's tragic? No. Yeah.
Oof. Wait, are we tied or are you winning?
Yeah.
I think you're winning.
Yeah, I'm winning. Am I? No, we're tied. 3-3.
Oh, sniped
2.
you. I sniped it.
Bro.
We're running out of spots here. Like I feel like this might converge to someone.
Yeah. Dude.
I'm just
here.
filling out this right side. I don't know how. Okay.
Okay, jeez.
Does this give hints? Like I wonder. Oh, maybe it's. Oh, okay. I think the dot pattern can sometimes give away where things are.
Okay.
So is that no? Okay. Maybe I don't understand.
Like, is it mean like there's one in this row, for example, like there? No.
I'm not telling.
I have no idea.
I'm not telling you. Okay, so what am I looking for? I have 2 2s left, and I have 2 1s.
I have 4 1s and 2 2s. It's crazy. No. You could definitely machine learn this though.
Yes.
Darn. You could definitely just like feed in configurations in games.
I feel like you have less. Oh, maybe like it feels like you have less surface area to explore.
Yeah, because I got the big ones first, but now I have all the small ones. I'm trying to figure out what the dot pattern means.
Um,
Mark verified empty cells. Ah, what does that mean?
Mark
Verified empty are the light ones, so I don't know if that means like it's secure. Yeah. No.
Yeah, did you figure something out?
I don't know. Maybe. Probably not.
Oof. Oh no.
I feel like it's like the end game of a chess game.
Or you don't know what's happening.
And yeah, and you're just like, oh, I gotta go speed. No. No.
Do you think there's
Can it?
do you think there are other games that would genuinely benefit from being like having some type of like superposition or some other type of quantum mechanical? Oh, did you beat me? Oh,
Yeah.
it's 2-0.
Um,
All right.
Cards. Definitely a card game. Anything that has like a finite number of things, and you're like your hand can be in a superposition of things. Like depending on the outcome of what someone plays, your cards can change. That'd be funny.
You're gonna sweep me, dude. We're gonna play chess.
No.
We're gonna play chess.
I know that's
no matter
what
happens.
Well, why do you think I chose? What is this?
This is Connect 4.
This connects 4. Okay.
It's my turn. So that's the correct
Opening.
Yeah.
Take the center.
Yeah, in my opinion. Yep.
Why did you get to start?
Because I'm losing. Okay. I guess that's problematic that you're up there. Ooh, that was a mistake. I think that was a blunder, to be honest. I think that was a huge blunder. I lost. Okay. Best 2 out of 3. Best 2 out of 3.
Oh, I start. Win the center.
I like that. I'm just blind, I guess. There are various versions of quantum chess. How does quantum chess work?
I have no idea.
What would that do?
I don't know.
What does I don't know if you mind expanding. Like what's quantum about quantum chess? Is it my turn? No, it's your turn.
I know it's mine. I just don't know what to play. Are you calculating?
Oh, is it my turn? Wait, where'd you go?
I went on top.
Oh, you've been inactive.
Best 2 out of 3 done.
No, I thought it was your turn, dude.
No take back. It says your turn or opponent's turn at the bottom.
I was looking at chat. Even though there's no movement in chat, I was looking at my phone.
All right. So your turn. All right. Canonical defense. The crisscross.
You have normal moves and quantum moves that only collapse with normal moves. Also, entangling the king and... Oh, you can entangle the king with other... Oh, that's interesting.
Oh, interesting. That's cool. It's your turn, by the way.
Guess we're going to have to say no to that one. Oh, my... All right, let's move on to chess. I am not seeing things today. That is so embarrassing how bad that went. Oh,
That's okay.
No. Oh no. Okay, play with a friend. We'll do a 5-minute control.
Sure.
5-minute control. Where are you, Night Joker?
I'm trying to see if I remember my password on my... Yeah, we're good. Invitation or other game that's going on. I just haven't.
Okay, okay, I'll click. Okay, I invite you.
Okay. Yeah.
All right. So revealing how bad I am at video games. I tend to be.
No, you're quite good. You're quite good at video games.
I tend to be good at things that I'm good at, and like everything else, I'm very, very bad. Like there's like no in between. And chess is one of those things that I'm just not very good at. I'm trying to learn, but
Oh.
I'm definitely trying to learn. Yeah, that's a fair response. That was a mistake.
Sure, but
I believe it was a mistake. I guess like I don't know what's actually happening.
does anyone know what's ever happening in chess?
I've been like I got entangle the king and the rook specifically. So what does entangling the king and the rook do? Like if the king gets attacked, it might switch positions with the rook or something? Interesting.
Oh.
What? Interesting.
You're just gonna takes.
Yeah. Takes. Little castle.
Little castle.
Little castle with the boys.
Oh, just punching at the thing.
It's probably the worst level of chess that has ever been streamed. Oh, that was a really good move. I did not see that. That's interesting, but too bad you can't do it.
Wait, why can't I grab your...
Because it'll reveal a check.
Oh, the king! Oh, that's lame. Well...
I feel like every physicist has played not a lot of chess, but you know. Did you learn chess growing up?
Me?
Yeah.
No, I did not.
We had a chess
clearly not.
We had
oh, cool.
We had a chess master coming to my elementary school. By the way, one of the things that I forgot to ask you, or like that didn't come up was, so like you started grad school in like a very strange time, right? Like in our department specifically, the physics community pre-COVID was like very, very close, but unfortunately due to COVID, you sort of joined the department in probably the most antisocial era of the department ever, right? So I'm just wondering, like, how do you, like, what, like, I don't even know what the question is. Like, do you think that's like affected your progress in grad school? Like, does that change anything in particular for you? Like, do you regret? Is that something you like that you wish wasn't particularly the case?
I wouldn't say so. I found our group was quite like willing to meet online and still have some form of um, like interest available.
Hmm.
So like you guys would always be around to do things. So it never felt like whenever we needed to um, uh, whenever we needed to um, meet, or if I had any questions or whatever, I could just reach out to you guys. You know what I mean? And a lot of research is primarily done on your own anyways, and it's good to like push yourself to do things how you see them. And that was like fine initially, but sorry, I had to think there.
No worries.
Well, that's annoying.
Yeah, you're running out of pieces.
It's because of the king had to move early.
Yeah, that's very, very true.
Yeah, that's unfortunate.
It is really too bad because like one of the best parts about grad school is sort of like the camaraderie, in some sense.
Yeah.
Like meeting other grad students, and then of course like the random conversations that you have with people when you're stuck on research, like being in the office with people is also very, very valuable.
Yeah, that's true. But at the same time, like, bro, my dog is like losing it. At the same time, it was, I don't know. You guys did a good job of allowing everyone to feel quite like there and interested. So it was quite good on my end. And then the group, I know Eric did quite a good job of making sure that everyone was I don't know, talking, and then you also made an effort too to reach out. So it was, I don't know, it was pretty good. It was pretty good overall, I find. I don't know. I guess for you started when you guys were talking to people and stuff.
Yeah, it was like we used to have these big physics house parties. Oh, that's interesting. I did not see that. We used to have these huge physics house parties, and sort of like you knew people like sort of across the department. You knew people in astrophysics. You knew people.
Yeah.
I don't know, in like experimental work and stuff like that. There was much more like community, and then that sort of like basically disappeared almost immediately as soon as COVID hit, which is understandable, I suppose, on some level, but it's unfortunate that people actually had to. I mean, finishing your undergrad that way, starting your undergrad that way, starting graduate school that way. It's just, you wish people didn't have to experience grad school in that late, I suppose.
Yeah, and I still have my PhD to grow a community like that as well. But from my undergrad, like, I mean, the last year of undergrad was also online, right?
Oh, so, true. Yeah.
So it wasn't too, like, I wasn't so surprised. I don't know. I was by that point, you're like in full throes of hey, my dog is losing it. Oh, whatever. I'm gonna lose this night. This is a stupid king move, man. A stupid king move. Fargo, why are you tripping?
You can have that night if you want him.
I got him.
I appreciate the fighting till the end.
Always gotta
take it.
Uh-huh.
Take it. Okay.
Oh.
All right.
Okay. I would like to be white. All right.
Okay. Okay. Interesting.
But I just debate you there. That's not the way it's supposed to go.
Do you think that starting during COVID and an undergrad during COVID has impacted your potential progress as a grad student at all?
Not. No, I don't think so.
You don't think?
I think no. I think during the undergrad, like as much as it's great to meet with people, like I mean, it really depends. It depends if you're talking in a professional capacity. I find there's certain things that you learn from others, which is undeniable. Like I agree with that, but I also don't. I also don't think that. Oh, hold on, my dog is like losing it. It's like, B. Yeah, sorry, it's hard to play chess and talk. No, I don't know. I'm not too to cut up. Let's do it. I'm not too worried about it, honestly. I don't think that like a lot of the I don't think that a lot of my development's been stunted, at least for that matter. It's more so been that it's just been like slowed down a bit, and like a lot of for the moment, there's some positive sides to having to have had that time to just focus on like learning things brute force. And I mean, I still got to go to class and everything, and that was fine. But I know personally that a lot of the learning is done later on. So
what do you mean later on?
So like for example, you'll learn something in class, but you won't necessarily it would be silly, would it?
I mean, yeah, that'd be as silly as you want.
Oh no, it wouldn't be. It wouldn't be.
Oh, interesting.
And so.
Oh, that was a bad move.
Yeah, I think so. Like a lot of the conversations that you're gonna have are. Oh wait, I need to think about this. A lot of the things you're going to learn and time you're going to spend. That's tragic. All the stuff that you're going to learn that's interesting is going to happen when you talk to people, and that only happens when you've understood things for a certain amount of time. So in my eyes, I've spent like a year learning some cool stuff, and now I feel very equipped and ready to talk about it in a confident manner.
I see. So you feel like you weren't ready to have productive conversations anyways. Oh, why didn't you just move your rook? Oh, never mind. That makes sense. That makes a lot more sense.
My king. Yeah.
I'm so confused. Oh, it's so embarrassing. Okay, so what do I want? Gotta somehow make up for the fact that I like hugely blundered.
Do it. Take the rook.
That makes sense. Imagine I did that. Take the pawn.
No.
You won't.
I will not. No, it's like the Irvin speech that he says. Like the membership is a reminder to us all: the courage is fallen. And fallen.
Ooh, what does that do? I see. Oh, never mind. I do not see. This might be over. Okay. What do I want here now? How do I not die? Is the open question that we are trying to solve.
The open question in the field is how do I not lose?
Yeah, I think the start of it is getting my king to safety. This is really bad. Oh, that's checkmate, I think. All right. All right. Best of three?
Yeah.
Oh, whoops. Oh, whoops.
Oh.
Rematch. Sorry, I accidentally declined. There you go.
Oh, I'm black for this one. Of course, you liar. Rematch, I promise, I promise.
Okay, let's avoid doing the exact same thing.
How are you supposed to play black up for this part? I only know the white opening. Like that's annoying. Question mark? Oh yeah, no, that's not good. That's such a bad idea. Why did I do that? That's so stupid. It's like this terrible, terrible move. Wow, that's really
So you don't think there's going to be like ripple effects going forward of
no,
these?
no, no. There's also like a lot of. I really do think that learning, like at least the way that I learn or interact with people, is that I need to spend a lot of time on my own to reflect on things, and then once I've built up a certain level of confidence, I feel really I feel really good about a certain. I'm trying not to sound vague. I think that it requires a certain amount of um, a certain amount of time spent understanding something and then kind of bringing it forward once I have the confidence to do so in a way that will be fruitful for me and not just me wondering on it. I think conversation is very important. It's very important to discuss and grow as a person and like in general. But I think this year, instead of considering it as something that could potentially be damaging, I could see it as an opportunity to develop something further, if that makes sense.
Yeah, that makes a lot of sense.
Just because it's like really easy to just be like, yeah, that's kind of poopy, you know,
I suppose I got
feel like it's not the best.
like I got a lot of like positive stuff out of, for example, going to the Perimeter Institute in person,
Yeah,
which is something that you never got to do.
No, that's true. That for that, I definitely agree. I think that there's a large component that needs to be about like going to colloquiums and spending time really getting your hands and being uncomfortable with things. I think that's really important. And I'm going to get that during my PhD, I believe. And I think that's going to be something that I'm going to even look more forward to. Like it's going to make it even more sweet, you know? And now I won't at least feel nervous about being like how much I know. Like at least I know I have some foundation that I could bring meaningfully without having to just like take a shot. You know what I mean? Oh, it's my turn.
Yeah. Yeah, that's fair.
I see. Very congested middle of the.
Am I missing something?
No, I'm just bad.
Okay, I was about to say. What?
I just didn't. I didn't even look at your rook, to be honest.
That's fine.
Hmm. Hmm. It's not what I should have done. Oh, that's the wrong move. It's the wrong move.
Why is it the wrong move?
I messed something up.
I see. Um.
Yeah. Hmm. I forgot I don't have my queen.
Interesting. Wait.
Oh, wow. Yeah, I didn't even see that.
Oh, wait. Oh, I'm blind. Wow, I thought that lined up in a way that it did not.
Why would you push that button?
Why would I push that pawn?
Yeah.
I mean, why not?
Why not? Mm. Just losing. Like, small position, just losing, but I just won't resign.
Fight till the end.
Yeah. No more pawns being pushed. Damn it. Yeah, this is it. This is it for me, my friends.
I will take everything from you. Oh my god, imagine I draw this. That'd be so embarrassing. Oh wait, that's
No, I think I had to stay back.
I think you lose by time here, yeah.
Yeah, I was gonna go take the. All right, GG.
All right, that was a
At
lot
least
of
I
fun.
won one of the games.
Thank you for coming on the stream. I hope there's
my
a lot
pleasure.
of informative things for people to hear. So thanks so much, and thank you for anyone who makes it all the way to the end of this.